Imagine standing at the very edge of reality itself, the boundary where space and time surrender their familiar rules, where light itself cannot escape, where the universe's most fundamental laws break down. You are poised at the event horizon of a black hole. A single step forward would pull you into a realm where time stretches like taffy, where space folds inward like an infinite origami, where the very atoms of your body would experience forces unlike anything in the known universe. This is not science fiction. These objects exist. They lurk in the darkness between stars, at the centers of galaxies, perhaps even wandering the void between cosmic structures. What really happens when matter crosses this threshold? When something or someone falls into a black hole? The answer seems deceptively simple at first. You would be stretched, compressed, and ultimately destroyed by gravitational forces so extreme they defy comprehension. This is what most physicists tell us. But there is another possibility, one that challenges our understanding of physics itself. What if, from your perspective as the one falling, you never actually reach the center? What if your descent becomes eternal? A journey without end, stretched across infinite time. Tonight, we explore one of the most profound paradoxes in all of physics. What truly happens when you fall into a black hole forever? We will trace humanity's evolving understanding of these cosmic devourers, from mathematical curiosities to observed reality. From Einstein's reluctant predictions to the first photograph of a black hole shadow in 2019, we'll examine what modern physics tells us about the nature of black holes, about the bizarre quantum effects that emerge at their boundaries, about the information paradox that continues to baffle the greatest minds in science. Most importantly, we'll confront the profound implications of what black holes reveal about our universe, about time, about the nature of physical law, about the limits of what we can know. The journey begins with a simple question that opens onto infinite complexity. What happens to you when you cross the boundary beyond which nothing should return? Does time itself end? Does consciousness persist in some form? Is there truly a point of no return, or might quantum mechanics offer some unexpected escape? These questions have occupied physicists for decades. They've inspired thought experiments that push at the boundaries of our understanding, that force us to confront the limits of known science. When we contemplate black holes, we confront the edges of human knowledge. We peer into abysses so profound, they challenge our most fundamental theories about reality. In these cosmic extremes, general relativity, our best theory of gravity, meets quantum mechanics, our best theory of the very small. And they disagree, dramatically. This disagreement isn't just an academic curiosity. It points to something missing in our understanding of the universe, something fundamental that we haven't yet grasped. Black holes are cosmic libraries where space and time behave in ways that seem impossible, where infinity isn't just a mathematical abstraction, but a physical reality you might encounter. In their darkness lies illumination, in their mystery, revelation, in their paradoxes, the seeds of the next great revolution in physics. The light from distant stars travels billions of years to reach us, but the interior of a black hole remains forever hidden, an ultimate cosmic secret kept behind a curtain of causality. Yet science has ways of probing even what cannot be directly observed, of inferring what lies behind veils that cannot be lifted, of testing theories against the patterns we can detect. Tonight, we will follow these clues. We will trace the outline of what cannot be seen. We will explore what happens when you fall into a black hole forever. And in doing so, we may glimpse something profound about the nature of existence itself, about the fabric of reality, about the boundary between the knowable and the forever unknowable. So settle in. Let your mind expand as we approach cosmic horizons. Breathe deeply as we contemplate the most extreme environments in our universe. Allow your thoughts to orbit these strangest of objects. For in understanding black holes, we understand something essential about our cosmos, about its structure, its limits, its underlying patterns, its deepest mysteries, and perhaps, in some small way, about our place within this vast and mostly dark universe, where light itself sometimes surrenders to gravity's relentless pull. Chapter 2. Echoes in the Darkness. Why are we drawn to black holes? What is it about these cosmic extremes that captures our imagination and refuses to let go? Perhaps it's because they represent the ultimate unknown, regions of space, where our understanding of physics breaks down completely, where the familiar rules no longer apply. Or perhaps it's because they speak to something deep within us, to our fascination with boundaries and what lies beyond them, to our desire to comprehend even the incomprehensible. Black holes remind us that the universe is stranger than we can imagine. That reality extends beyond what our minds, evolved on the gentle surface of Earth, can readily grasp. Yet in their very strangeness, black holes offer a kind of cosmic perspective, a reminder that our daily concerns exist within a universe of almost unimaginable scale and complexity. There's something oddly comforting in this, in knowing that while we may never understand everything, we can still approach these mysteries with wonder and curiosity rather than fear. The science of black holes isn't just about distant cosmic objects. It's about fundamental questions that touch on the nature of existence itself. What is time, really? Is information ever truly lost? Can something be both precisely predicted by physics and fundamentally unknowable? These questions ripple outward from black hole physics to touch everything from quantum computing to the nature of consciousness, from cosmology to philosophy. When we contemplate a journey into a black hole, we're really contemplating the limits of experience itself, the boundaries of what it means to exist as a conscious entity in this universe. From outside a black hole, an observer would never see you cross the event horizon. Time dilation would stretch your image, frozen at the boundary, growing ever dimmer, but never quite disappearing. Yet from your perspective as the traveler, nothing special would happen at the horizon itself. You would cross what seems like ordinary space, unaware that you've passed a point of no return. This discrepancy between perspectives reveals something profound about reality. That different observers can have fundamentally different, yet equally valid, experiences of the same events. The mathematics tells us that once inside, all paths lead inevitably toward the singularity at the center. The future becomes as fixed and unavoidable as the past. Yet some theorists propose that quantum effects might alter this classical picture, that the interior might be more complex than Einstein's equations alone would suggest. Perhaps the most profound aspect of black hole physics is how it forces us to confront the limits of what we can know. The humbling recognition that some answers may lie permanently beyond our reach. This isn't cause for despair, but for wonder, for recognizing that the universe is not obligated to make complete sense to minds that evolved to find edible berries and avoid predators. There's a special kind of peace in acknowledging these limits, in embracing the mystery while still striving to understand what we can. Black holes teach us that not all questions have answers, at least not answers that would make sense to beings like ourselves, bound by time and limited perspective. They remind us that the universe operates according to its own logic, that human intuition is just that, human, a product of our particular evolutionary history and cognitive architecture. And yet, remarkably, mathematics and physics allow us to extend our understanding far beyond what intuition alone could grasp, to model and predict phenomena we could never directly experience. When Stephen Hawking discovered that black holes should emit radiation and eventually evaporate, he revealed yet another layer of their paradoxical nature, that what seemed eternal might be temporary after all. This discovery connected gravity, quantum mechanics, and thermodynamics in unexpected ways. It suggested deep relationships between seemingly separate domains of physics. It hinted at underlying patterns still waiting to be fully understood. A unified theory that might someday reconcile the apparent contradictions in our current models. Until then, black holes remain windows into the unknown. Cosmic laboratories where the most extreme conditions test our theories to their breaking points. They challenge us to think beyond the familiar, to stretch our minds toward concepts that may initially seem impossible or contradictory. In contemplating black holes, we engage in one of humanity's noblest pursuits, the attempt to understand our universe not just as it appears to our limited senses, but as it truly is. There's something deeply human in this reaching toward comprehension, in this refusal to be bounded by the limits of our direct experience. And there's something profoundly humbling in recognizing how much remains unknown. How much may always remain unknown. The journey into a black hole that we're exploring tonight is partly literal, a thought experiment about actual cosmic objects, and partly metaphorical, a journey toward the edges of knowledge itself. As we follow this path together, remember that uncertainty need not be frightening, that not knowing can be as valuable as knowing, that mystery itself can be a form of truth. Chapter 3. Shadows from Enlightenment. The story of black holes begins long before anyone called them by that name. It starts with light, gravity, and the attempt to understand how they relate to one another. In 1687, Isaac Newton published his theory of universal gravitation. He described gravity as a force that acts instantly across any distance, a force that governs falling apples and orbiting planets alike. Newton's equations worked remarkably well for predicting the motions of celestial bodies, but they contained no upper limit on gravitational strength. Nothing to prevent the existence of objects so massive that nothing could escape them. In 1783, John Michell, an English clergyman and scientist, took Newton's ideas to their logical conclusion. He calculated that a star 500 times the size of our sun would have a gravitational pull so strong that light itself could not escape. Michell called these hypothetical objects dark stars. He suggested they might be detected by observing stars that appear to orbit around an invisible companion. Independently, Pierre-Simon Laplace, a French mathematician, reached similar conclusions in 1796. His corps obscurs, or dark bodies, were essentially the same concept, objects whose gravity trapped even light. These 18th century insights were remarkable, but they were based on the understanding of light as a particle subject to gravitational forces. The wave theory of light, which gained prominence in the 19th century, temporarily derailed this line of thinking. For over a century, the concept of objects with inescapable gravity remained a mathematical curiosity rather than a serious astronomical proposal. The universe seemed to operate within more moderate parameters. Then came Albert Einstein and his revolutionary theory of general relativity in 1915. Einstein reimagined gravity not as a force, but as a curvature of space-time itself. According to general relativity, massive objects don't pull on other objects directly. Instead, they bend the fabric of space and time around them, creating paths that other objects naturally follow. Just weeks after Einstein published his theory, Karl Schwarzschild, a German physicist serving in World War I, found a solution to Einstein's complex equations. He did this while on the Russian front, shortly before his death. Schwarzschild's solution described a spacetime around a perfectly spherical mass. It contained a peculiar feature, a radius at which time would appear to stand still when viewed from far away. At this radius, now called the Schwarzschild radius, Einstein's equations predicted that space and time would curve so extremely that nothing, not even light, could escape. Einstein himself was skeptical of this implication. He published a paper in 1939 attempting to prove that such objects could not physically form in nature. Meanwhile, other physicists continued exploring these mathematical singularities. In 1939, Robert Oppenheimer and his student, Arlen Snyder, calculated that massive stars could indeed collapse to form what we now call black holes. Their work suggested that a dying star, having exhausted its nuclear fuel, might collapse under its own gravity to a point where no known force could prevent it from being crushed to infinite density. From the perspective of a distant observer, they calculated, the star's collapse would appear to slow and ultimately freeze at the Schwarzschild radius. Its light would redshift to invisibility. But from the perspective of matter falling with the collapse, the process would continue until all the star's mass was compressed into a singularity, a point of zero volume and infinite density. These ideas remained largely theoretical curiosities for decades. Without observational evidence, many astronomers considered black holes to be mathematical artifacts rather than real astronomical objects. The term black hole itself wasn't coined until 1967, when American physicist John Wheeler used it during a lecture. The name captured both the object's appearance and its gravitational behavior. As Wheeler later explained, it is a black hole because light cannot escape from it, and it is a hole because something can fall into it. But nothing can ever come back out. The simplicity and vividness of the term helped popularize the concept. It gave physicists and astronomers a clear label for these extreme objects that had previously been described with more technical terminology. By the 1960s, theoretical work on black holes was accelerating. Roger Penrose and Stephen Hawking developed mathematical proofs about singularities, while others explored the strange physics of black hole boundaries. These theoretical developments coincided with advances in observational astronomy that would soon provide the first compelling evidence that black holes weren't just mathematical curiosities. They actually existed in our universe. The stage was set for black holes to move from theoretical prediction to observed reality, from mathematical possibility to astronomical fact, from scientific speculation to cosmic truth. Chapter 4. Glimpsing the invisible. How do you find something that, by definition, cannot be seen? Something that traps all light and radiation that crosses its boundary? Something that manifests only through its effects on surrounding space? This was the challenge astronomers faced in their search for black holes. They needed to detect objects that are, in a very real sense, invisible. The first promising candidate emerged in the 1960s. Cygnus X1, a powerful source of X-rays in the constellation Cygnus, behaved in ways that suggested the presence of something extraordinarily compact and massive. Observations revealed that Cygnus X1 consisted of a visible blue supergiant star orbiting around an unseen companion. The X-rays appeared to be coming from hot gas being pulled from the visible star. This gas formed an accretion disk around the invisible object, heating up to millions of degrees as it spiraled inward. Only an object with extraordinary gravitational pull could generate such energetic phenomena. By the 1970s, detailed measurements of the system indicated that the invisible companion had about 15 times the mass of our Sun, yet occupied a tiny region of space. This was too massive to be a neutron star, which physicists calculated couldn't exceed about 3 solar masses without collapsing further. The evidence pointed strongly toward a black hole. Similar systems were soon discovered elsewhere in our galaxy. Objects too massive and compact to be anything but black holes, revealed by their gravitational effects on visible companions or surrounding gas. But stellar mass black holes formed from collapsed stars were just the beginning. Theory predicted something even more extreme. Supermassive black holes millions or billions of times more massive than our Sun. These cosmic monsters would likely reside at the centers of galaxies, including our own Milky Way. Their immense gravitational influence would shape the motion of stars and gas across thousands of light years. In the 1990s, astronomers using the Hubble Space Telescope observed something remarkable in many galactic centers. Disks of gas and stars rotating at enormous speeds around central regions of intense gravitational pull. The galaxy M87 showed particularly compelling evidence. Gas near its center was orbiting at speeds suggesting a central mass of about 3.5 billion solar masses, concentrated in a region smaller than our solar system. Closer to home, astronomers tracking stars orbiting the center of our own Milky Way observed them following elliptical paths around a point called Sagittarius A*, pronounced Sagittarius A star. These stellar orbits revealed the presence of an object with about 4 million times the mass of our Sun, yet confined to a region smaller than the distance between the Sun and Mercury. One star, designated S2, completes an orbit around this invisible mass in just 16 years, reaching speeds of over 25 million kilometers per hour at its closest approach. Only a supermassive black hole could explain these observations. Nothing else known to physics could concentrate so much mass in such a small volume without collapsing completely. Meanwhile, theoretical understanding of black holes continued to deepen. Stephen Hawking's discovery that black holes should emit radiation, now called Hawking radiation, suggested they weren't completely black after all. This radiation would be extremely faint for large black holes, but would gradually lead to their evaporation over unimaginably long timescales, roughly 1,067 years for a black hole with the mass of our Sun. The quest to actually see a black hole directly, or rather, to see the shadow it casts against background light, required a telescope the size of Earth. This seemingly impossible goal led to the Event Horizon Telescope Project. By synchronizing radio telescopes across the globe, astronomers created a virtual dish with the resolving power to image the immediate environment around a black hole's event horizon. In April 2019, the world saw the first direct image of a black hole, the supermassive black hole at the center of galaxy M87, a glowing ring of light surrounding a dark central shadow. That historic image confirmed what decades of indirect evidence had suggested. Black holes are real. They exist not just as mathematical solutions or theoretical constructs, but as actual physical objects in our universe. The distance scales involved are mind-boggling. The M87 black hole lies 55 million light-years from Earth. Its mass is 6.5 billion times that of our Sun. Its event horizon spans a diameter larger than our entire solar system. In 2022, astronomers revealed a similar image of Sagittarius A*, the supermassive black hole at the center of our own galaxy. Though 1,000 times less massive than M87's black hole, it's also 1,000 times closer to us. These direct observations marked a triumph of human ingenuity and scientific collaboration. They transformed black holes from theoretical predictions to observed reality, from mathematical possibility to photographic fact. But they also deepened the mystery. For while we can now see the environments around black holes, their interiors remain hidden behind event horizons, boundaries beyond which no information should be able to return. Or so the classical theory tells us. Yet quantum mechanics suggests a different story. One where information might not be truly lost, where the interior might be more complex than a simple point of infinite density. As we prepare to venture beyond the event horizon in our exploration, we stand at a boundary not just of space, but of knowledge itself. At the frontier where our most successful physical theories begin to contradict each other. What happens if you fall into a black hole forever? To answer this question, we must now confront the deepest paradoxes of modern physics. The places where space and time behave in ways that challenge our fundamental understanding of reality. Chapter 5. The paradoxes of the fall. As we approach the event horizon in our thought experiment, we encounter the first of many profound contradictions. From the perspective of someone watching from a safe distance, you would appear to slow down as you near the boundary. Time itself seems to stretch. Your movements become increasingly sluggish. Your clock ticks ever more slowly. The light from your spaceship shifts toward the red end of the spectrum. Eventually, to the distant observer, you appear frozen at the event horizon itself. A fading image, growing dimmer but never quite disappearing. An eternal monument to your journey, suspended at the boundary between normal space and whatever lies beyond. And yet, from your perspective as the traveler, nothing unusual happens as you cross the event horizon. No alarm sounds. No barrier appears. No sudden change marks your passage from the outside universe to the black hole's interior. This discrepancy isn't a flaw in our understanding. It's a feature of how space and time behave in extreme gravitational fields. A consequence of the relativity of simultaneity and reference frames that Einstein revealed. Both perspectives are equally valid. Both describe the same physical reality, yet they seem irreconcilably different, highlighting the first great paradox of black holes, the apparent contradiction between different observers' experiences. But this is just the beginning of the strangeness. Once past the event horizon, all paths through space-time lead inexorably toward the singularity at the center. The future becomes as fixed and unavoidable as the past. Space and time, in a sense, switch roles. Movement through space toward the singularity becomes as inevitable as movement through time toward the future. The direction that was once inward becomes effectively forward in time. This profound reconfiguration of space-time structure means that once inside, escape becomes impossible, not just practically but logically, like trying to travel backward in time under normal conditions. Yet here we encounter another paradox. Classical physics predicts that at the center of a black hole lies a singularity, a point of infinite density and zero volume where space-time curvature becomes infinite. At a singularity, our equations break down completely. The mathematics of general relativity produces infinities, which physicists interpret as a sign that the theory itself has reached its limits of applicability. Most physicists believe these infinities indicate that a more comprehensive theory, one that unifies gravity with quantum mechanics, is needed to describe what truly happens at the core of a black hole. This brings us to perhaps the most profound black hole paradox of all, the information paradox first identified by Stephen Hawking in the 1970s. Quantum mechanics insists that information cannot be destroyed. The precise quantum state of every particle must in principle be traceable backward and forward through time, even if practically impossible to track. Yet black holes appear to destroy information. Once something crosses the event horizon and reaches the singularity, all its distinguishing characteristics seem erased. Only its mass, charge, and angular momentum affect the black hole. This apparent contradiction between quantum mechanics and general relativity reveals a deep incompatibility between our two most successful physical theories. They cannot both be completely correct as currently formulated. The information paradox intensified in 1974, when Hawking discovered that black holes should emit radiation and gradually evaporate. This raised an even more troubling question. What happens to the information contained in a black hole once it's gone? If the radiation is purely random, as initially calculated, then information is permanently lost, violating a fundamental principle of quantum mechanics. If the information somehow escapes, how does it get out past the event horizon? Various solutions have been proposed. Perhaps information is encoded on the event horizon itself, like a hologram. Perhaps it leaks out gradually in subtle quantum correlations within the Hawking radiation. Perhaps the interior of a black hole isn't a simple singularity, but a complex structure, maybe even a portal to another region of space-time, as suggested by some interpretations of the mathematics. In 2019, physicist Don Page calculated that information might escape from black holes through quantum hair, subtle quantum effects that preserve information about what fell in. But this remains highly speculative. Another possibility is that quantum effects prevent true event horizons from forming in the first place. Instead, there might be apparent horizons that temporarily trap light but eventually allow information to escape. Or perhaps, as some string theorists suggest, falling into a black hole is physically equivalent to being immersed in a hot bath of quantum particles. Different description, same physics, a concept called the holographic principle. This principle suggests that all the information about what happens inside a three-dimensional volume might be completely encoded on its two-dimensional boundary, like a hologram storing 3D information on a 2D surface. If true, then perhaps the information paradox is resolved because information is simultaneously inside the black hole and encoded on its event horizon. Never truly lost, just transformed and stored in a different form. Yet another approach comes from quantum gravity theories like loop quantum gravity, which suggests that space-time itself has a granular structure at the smallest scales, preventing true singularities from forming. In these models, matter falling into a black hole might eventually emerge in another region of space-time, perhaps even another universe, through what's called a white hole, a theoretical time-reversed black hole. The existence of such connections, called Einstein-Rosen bridges or wormholes, was suggested by the mathematics of general relativity decades ago. But whether they can physically exist remains highly speculative. Recently, some theorists have proposed connections between quantum entanglement, Einstein's spooky action at a distance, and wormholes. Perhaps these phenomena are two descriptions of the same underlying physics. This VOEPR conjecture, named after papers by Einstein, Rosen-Podolsky, and others, suggests that entangled particles might be connected by microscopic wormholes, unifying concepts from quantum mechanics and general relativity. If true, this could have profound implications for black hole physics. It might mean that information falling into a black hole remains connected to the outside universe through quantum entanglement. But what does all this mean for our original question? What happens if you fall into a black hole forever? The honest answer is that we don't know for certain. The contradictions between our best physical theories leave room for multiple possibilities, each with its own philosophical and scientific implications. In the classical picture, you would experience nothing unusual at the horizon, but would inevitably be destroyed at the singularity. Your journey would end in a region where physics itself breaks down. But quantum effects might radically alter this picture. Perhaps you would encounter a granular structure of space-time rather than a true singularity. Perhaps information about your journey would be preserved in some form. Perhaps the most profound realization is that black holes force us to confront the limits not just of our current physical theories, but of what it means to have a physical theory at all. When different reference frames give contradictory descriptions of the same events, when causality itself breaks down, when our most fundamental theories disagree, we enter territory where conventional understanding falters. Yet in this uncertainty lies tremendous possibility. Black holes are cosmic laboratories where the most extreme conditions test our theories to their breaking points, where future breakthroughs in physics may well emerge. Chapter 6. Stories in the dark, the human mind abhors a vacuum. Where knowledge ends, imagination begins. Where science offers uncertainty, mythology rushes to fill the gap. Black holes, existing at the frontier of understanding, have become magnets for misconception and myth. Perhaps the most common misconception is that black holes act like cosmic vacuum cleaners, sucking in everything around them. This image pervades popular culture, but fundamentally misrepresents their nature. In reality, a black hole's gravitational pull follows the same inverse square law as any other massive object. Replace our sun with a black hole of equal mass, and Earth's orbit would remain unchanged. The difference emerges only when you approach very close to a black hole. Only then does its compact nature create gravitational fields strong enough to prevent escape, even for light itself. Another persistent myth portrays black holes as tunnels or portals to other universes or distant parts of our own. While mathematically intriguing, this remains highly speculative, not established science. The popular image of getting spaghettified, stretched into a thin stream of matter, as you fall into a black hole, contains truth but often misses important details about when and how this would occur. For a stellar mass black hole, tidal forces would indeed tear you apart long before reaching the event horizon. But for a supermassive black hole, you might cross the horizon relatively intact, experiencing extreme stretching only as you approach the center. Many visualizations show black holes as funnel-shaped depressions in a two-dimensional fabric, like a bowling ball on a trampoline. While helpful for understanding certain aspects of curved spacetime, these images can be misleading. Real black holes exist in three-dimensional space, with time as a fourth dimension. The actual curvature occurs in this four-dimensional spacetime, something inherently difficult to visualize. Some popular accounts suggest that time stops completely at the event horizon. This isn't quite right. From your perspective as a falling observer, time would continue to flow normally as you cross the boundary. The time dilation effect is relative. It's observed by distant witnesses watching your journey, not experienced by you. This distinction is crucial for understanding what falling into a black hole forever might actually mean. Science fiction often portrays black holes as gateways to parallel universes or time travel opportunities. While mathematics allows for such possibilities, they remain in the realm of speculation, not established physics. The viral image that captured public imagination in 2019, our first direct photograph of a black hole, is itself frequently misunderstood. It doesn't show the black hole itself, which emits no light to be photographed. Rather, it shows hot gas orbiting the black hole, with the central dark region representing the shadow cast by the black hole against this background. It's an extraordinary scientific achievement, but not literally a picture of the black hole. Some describe black holes as tears in the fabric of space-time. This poetic language evokes their extreme nature, but doesn't accurately represent current understanding. They are regions of intense curvature, not actual tears or holes. The common claim that nothing can escape a black hole requires qualification in light of Hawking radiation. Through quantum effects, black holes do emit particles and will eventually evaporate, though on timescales far longer than the current age of the universe. Animations often show material spiraling directly into a black hole. In reality, matter usually forms an accretion disk and spirals inward gradually as it loses energy through friction, heating up to millions of degrees in the process. Some speculate that miniature black holes might be created in particle accelerators, like the Large Hadron Collider. While theoretically possible, such microscopic black holes would evaporate almost instantly through Hawking radiation. The fear that such experiments could create Earth-devouring black holes represents a profound misunderstanding of both the energies involved and the physics of how black holes grow and interact with matter. There's a common belief that black holes will eventually consume everything in the universe. The expansion of space itself prevents this. Distant galaxies are moving away from us faster than their black holes could ever grow or travel. Some spiritual and pseudoscientific traditions ascribe mystical properties to black holes, claiming they generate special energies or consciousness. These claims lack scientific foundation, though the genuine mysteries are wondrous enough. The notion that information sent into a black hole could be used for faster-than-light communication misunderstands both relativity and quantum mechanics. Black holes don't circumvent these fundamental limits. Many visualizations show black holes as completely dark against a starry background. In reality, gravitational lensing would create a complex pattern of distorted star images around the black hole. Light from stars behind the black hole would be bent around it, creating multiple images or even complete Einstein rings. The visual appearance would be stranger and more beautiful than simple darkness. The misconception that falling into a black hole would allow you to see the entire future history of the universe misunderstands the nature of time dilation. Your proper time, your experienced time, continues to flow forward normally. What you would see looking outward depends on complex factors, including the black hole's rotation and your own trajectory. But you wouldn't witness the entire cosmic future unfold before you. If you somehow survived crossing the event horizon of a rotating black hole, you might encounter what theorists call an inner horizon, a boundary where predictability breaks down even more completely than at the central singularity. Beyond this inner horizon, some solutions to Einstein's equation suggest you might encounter negative energy densities, closed time-like curves, potential time machines, or bridges to other regions of spacetime. However, most physicists believe quantum effects would destabilize these exotic features. The classical mathematics allows for them, but more complete theories might reveal them to be physically impossible. Stephen Hawking once wagered that black holes destroy information completely, then conceded the bet in 2004. This illustrates how even the greatest minds have revised their thinking about black holes over time. The firewall paradox proposed in 2012 suggests that reconciling quantum mechanics with general relativity might require the event horizon to be a region of intense energy, contradicting Einstein's prediction that nothing special happens there. If true, anyone falling into a black hole would encounter a wall of fire at the horizon rather than passing through uneventfully. This remains one of many unresolved theoretical conflicts in black hole physics. Perhaps most fundamentally, the very question, what happens inside a black hole, might be meaningless in some interpretations. If information can't escape, then arguably nothing that happens inside can be considered part of physical reality. This philosophical position, that only observable phenomena constitute reality, raises profound questions about the nature of existence itself. Black holes thus challenge not just our physics, but our metaphysics. What makes black holes so fertile ground for both scientific investigation and mythological thinking is precisely this quality. They exist at the boundary of the knowable, where observation ends and inference begins. In this twilight region between established science and informed speculation, we must tread carefully, distinguishing between solid theory, reasonable extrapolation, and pure fantasy requires both scientific literacy and intellectual humility. Chapter 7. Cosmic Consequences. Why does any of this matter? Beyond theoretical interest, what difference does it make whether information survives a plunge into a black hole or vanishes forever? Whether singularities truly exist or are replaced by exotic quantum structures? The stakes are nothing less than our fundamental understanding of reality. The resolution of black hole paradoxes will likely reveal deep truths about the nature of space, time, matter, energy, and information. This isn't merely academic. Throughout history, seemingly abstract theoretical questions have led to transformative technologies. Quantum mechanics, once purely theoretical, now underlies everything from smartphones to medical imaging. If information truly cannot be destroyed, as quantum mechanics insists, then everything that has ever fallen into a black hole remains encoded somewhere, somehow, even if inaccessible to us. This suggests a universe where causality and history have an absolute character, where the past is never truly erased, only transformed, where the book of nature, once written, cannot have its pages torn out. Conversely, if information can be permanently lost, we live in a fundamentally different reality, one where perfect prediction is impossible, even in principle, where the past may leave no trace on the future. This question connects directly to the nature of time itself. Is time fundamental or emergent from more basic quantum processes? Do past, present, and future all exist simultaneously in a block universe? Or does reality unfold moment by moment? Black hole physics suggests possible answers. If information eventually escapes through Hawking radiation, this implies a universe where past states remain deterministically connected to future states, preserving causality across cosmic timescales. The practical implications extend to cosmology. Our universe likely contains billions of black holes, from stellar remnants to the supermassive behemoths at galactic centers. Their behavior shapes cosmic evolution on the grandest scales. Recent observations suggest supermassive black holes formed surprisingly early in cosmic history, challenging our models of galaxy formation. Understanding their origins and growth requires resolving theoretical questions about their nature. Black holes also serve as cosmic laboratories for testing potential theories of quantum gravity. Attempts to reconcile general relativity with quantum mechanics into a single unified framework. Any successful theory of quantum gravity must explain what happens at a black hole center, must resolve the information paradox, must tell us whether singularities physically exist or are merely mathematical artifacts. Competing approaches, string theory, loop quantum gravity, causal set theory, and others make different predictions about black hole interiors. Observational tests might eventually distinguish between these candidates. This connects to the quest for a theory of everything, a comprehensive framework unifying all fundamental forces. Black holes, where extreme gravity meets quantum effects, provide crucial testing grounds for such theories. Beyond theoretical physics, black holes influence practical astronomy. Gravitational waves from black hole mergers, first detected in 2015, opened an entirely new window on the universe, allowing us to hear cosmic events. These ripples in spacetime carry information about black holes' masses, spins, and orbital dynamics. They've already revealed unexpected populations of black holes and will likely yield further surprises as detection sensitivity improves. The imaging of black hole shadows by the Event Horizon Telescope has similarly transformed observational astronomy. Future observations will test general relativity with unprecedented precision and might reveal quantum effects. Black holes also serve as cosmic accelerators, powering the most energetic phenomena in the universe. Active galactic nuclei, supermassive black holes devouring surrounding matter, can outshine all the stars in their galaxies. The jets of particles they emit, accelerated to nearly light speed, stretch across millions of light years. They influence galaxy evolution, star formation, and the distribution of matter and energy throughout the cosmos. For human futures, understanding black holes might eventually enable technologies beyond our current imagination. If quantum entanglement and wormholes are indeed connected, this might lead to new communication or computing paradigms. The extreme physics near black holes might someday be harnessed for energy generation, propulsion, or information processing. What seems purely theoretical today might become practical in centuries to come. More immediately, astronomical observations of matter orbiting black holes allow us to test physics under conditions impossible to create in laboratories. These natural experiments probe the limits of our most fundamental theories. In a deeper sense, black holes challenge our place in the cosmic order. They remind us that the universe operates according to principles that may forever exceed human intuition, evolved as it was on the gentle surface of Earth. They confront us with regions of spacetime where causality, locality, and unitarity, principles we take for granted, come into apparent conflict, where reality itself seems to reach a breaking point. Yet, rather than discouraging scientific inquiry, these challenges inspire it. The history of physics shows that apparent contradictions often signal the emergence of deeper understanding, more comprehensive theories. This pattern has repeated throughout scientific history. Newton's mechanics gave way to Einstein's relativity. Classical physics yielded to quantum mechanics. Each revolution preserved what worked in the previous framework while transcending its limitations. The paradoxes of black holes suggest we stand on the cusp of another such revolution, one that might reconcile quantum mechanics and general relativity, one that might transform our understanding of space, time, and reality itself. Some physicists speculate this new framework might reveal space-time itself to be emergent rather than fundamental, a macroscopic approximation arising from deeper quantum processes, like temperature, emerges from molecular motion. Others suggest information might be the truly fundamental quantity, more basic than space, time, or energy. In this view, reality is ultimately composed not of particles or waves, but of bits. Yes, no answers to experimental questions. These possibilities connect black hole physics to profound philosophical questions about the nature of existence, about whether mathematics discovers or invents reality, about the relationship between mind, matter, and information. They even touch on questions of cosmic destiny. If black holes eventually evaporate completely, returning their energy to the cosmos, what does this mean for the ultimate fate of a universe filled with them? Will the information they've absorbed be restored to the broader universe, preserving the complete record of cosmic history? Or will some aspects of reality be permanently lost, erasing portions of the cosmic story? As we contemplate falling into a black hole forever, we're really asking about the deepest structure of reality, about whether infinity is physical or merely mathematical, about whether existence has an absolute or relative character. The answers will likely transform physics as profoundly as quantum mechanics and relativity did a century ago. They may reveal a reality stranger and more beautiful than we can currently imagine. And they remind us of the extraordinary privilege of consciousness, of being the part of the cosmos that can contemplate its own nature, that can ask questions about black holes and infinity, that can seek to understand what it means to exist. As we prepare to explore the most speculative frontiers of black hole physics in our final section, remember that we stand at the edge of knowledge, where established science meets informed conjecture. What lies beyond that boundary? What happens at the central singularity? What occurs in the deepest interior of a black hole? What would it truly mean to fall into one forever? These questions take us to the limits of current understanding, to realms where different theories make contradictory predictions, where the rules of reality as we know them begin to break down completely. Chapter 8: Doorways Through Impossibility, as we approach the ultimate question of what truly happens when you fall into a black hole forever. Three compelling theories emerge from the frontiers of theoretical physics. Each offers a different window into the nature of reality at its most extreme. The first theory, rooted in classical general relativity, suggests that your journey would indeed continue toward the singularity. Space-time would stretch and compress in increasingly extreme ways as you approach the center. In this view, the mathematical singularity represents a genuine end to space and time, a boundary beyond which physics as we know it simply stops. Your journey would terminate at this boundary, your matter adding to the black hole's mass. But many physicists find this unsatisfying. Singularities, where quantities become infinite, often signal the breakdown of a theory rather than representing physical reality. They suggest our understanding is incomplete. This leads to the second major theory, that quantum gravity effects prevent true singularities from forming. Instead, space-time might have a fundamental graininess or quantum foam structure at the smallest scales. In this quantum perspective, what appears as a singularity from far away resolves into a complex structure when viewed up close, much as a smooth-looking beach reveals individual sand grains upon closer inspection. Various approaches to quantum gravity, string theory, loop quantum gravity, asymptotic safety, and others, all suggest mechanisms by which infinities might be tamed. Though they differ in details, all predict a regularization of the singularity. In some versions of loop quantum gravity, for instance, the collapse that would create a singularity bounces instead, perhaps creating what's called a white hole, a time-reversed black hole that ejects matter rather than consuming it. If true, falling into a black hole might eventually lead to emerging from a white hole, possibly in another region of our universe, or perhaps in another universe entirely. Your fall would not be truly forever, but would have a destination. String theory offers another perspective. In this framework, black hole interiors might contain tangles of tiny strings that encode all information about what fell in. The apparent singularity would be replaced by this fuzzball of strings. This would mean that different black holes, having consumed different matter and energy, would have different interiors. Your journey would depend on the specific history of the particular black hole you entered. A third major theoretical approach centers on holography, the surprising mathematical finding that all the information contained in a volume of space can be encoded on its boundary surface. Applied to black holes, this suggests that everything happening in the interior might be completely described by quantum effects at the event horizon. The three-dimensional reality inside might be projected from this two-dimensional boundary. If true, falling into a black hole might be physically equivalent to becoming entangled with the quantum fields at the horizon. Two descriptions of the same physics, much as liquid water and steam are two phases of the same substance. This connects to the controversial firewall hypothesis proposed by physicist Joseph Polchinski and colleagues in 2012. They argued that preserving quantum principles might require the event horizon to be a region of intense energy. In this scenario, rather than passing smoothly through the event horizon, you would encounter a wall of fire, high-energy particles that would destroy you before any journey to the center could begin. This firewall would arise from quantum entanglement between Hawking radiation particles, escaping the black hole and their partners falling in. Breaking this entanglement would release energy, creating the firewall. Not all physicists accept this conclusion. Some, like Leonard Susskind, have proposed that quantum effects might make the interior of a black hole much larger than classical physics suggests, perhaps even infinite. In this black hole complementarity view, information could be both destroyed at the singularity from the perspective of someone falling in and preserved in Hawking radiation from the perspective of someone watching from outside. These seemingly contradictory descriptions would be complementary in a quantum sense, different but equally valid ways of describing the same physical reality, much like the wave-particle duality of light. Each of these theoretical frameworks has strengths and weaknesses. Classical general relativity has been repeatedly confirmed by observation, but breaks down at singularities. It cannot be the complete story. Quantum gravity approaches offer ways to resolve singularities, but remain largely speculative. Most lack definitive observational tests that could confirm or refute them, putting them at the boundary between physics and mathematics. Holographic models elegantly resolve some paradoxes, but introduce conceptual challenges about the nature of space itself. Is three-dimensional space fundamental, or merely an emergent approximation of deeper quantum reality? What complicates matters further is that these approaches need not be mutually exclusive. Elements of each might be incorporated into whatever unified theory eventually emerges from current theoretical explorations. Perhaps the most profound insight comes not from choosing between these theories, but from recognizing what they collectively reveal, that space, time, and matter as we experience them may be approximations of a deeper reality. Much as Newtonian physics works perfectly well for everyday situations, but must yield to relativity and quantum mechanics in extreme conditions, our entire concept of space-time may be an approximation valid only in certain regimes. Black holes force us to confront this possibility directly. They suggest that what we call falling forever might involve a transition from space-time as we know it to something more fundamental, a substrate from which space-time emerges. In this view, asking what happens inside a black hole might be like asking what's north of the North Pole. It assumes a framework that may not extend into that region in any meaningful way. Yet unlike the North Pole, which we can visit and photograph, the interior of a black hole remains forever hidden behind its event horizon. Whatever happens there cannot be directly observed from outside. This observational barrier means that choosing between competing theories ultimately requires indirect evidence. We must look for subtle consequences of interior physics that might manifest in observable phenomena. As we'll explore in the next chapter, new astronomical instruments and techniques are beginning to provide such evidence. They're allowing us to test theories of black hole physics with unprecedented precision. What they reveal may ultimately answer our central question: what happens if you fall into a black hole forever? Whether your journey would end at a singularity, bounce through to another reality, or transform into something else entirely. The answer, when it comes, will likely transcend our current categories of thought. It will reveal not just the fate of a hypothetical traveler, but the fundamental nature of reality at its most extreme. For now, we navigate between competing theories, each offering a different window into the unknown, each representing humanity's best attempt to comprehend the incomprehensible, to imagine what lies beyond the event horizon of understanding. Chapter 9. Peering Through the Veil. How do we test theories about places we can never visit? How do we gain knowledge about regions hidden behind event horizons? The answer lies in increasingly sophisticated observations that probe the environment around black holes. The Event Horizon Telescope's groundbreaking images revealed the shadow cast by supermassive black holes against the glowing background of accreting matter. These images confirm predictions of general relativity with remarkable precision. The ring of light surrounding the dark central region matched Einstein's predictions about how gravity bends light paths. The size and shape of the shadow aligned with calculations based on the black hole's estimated mass. But these images, revolutionary as they are, show only the environment immediately surrounding the black hole. They don't directly reveal what happens beyond the event horizon or at the putative singularity. For that, we need additional tools and techniques. Gravitational waves, ripples in spacetime produced by violent cosmic events, offer one promising avenue for probing black hole physics more deeply. First detected in 2015, gravitational waves from merging black holes carry information about their masses, spins, and orbital dynamics. They also contain subtle imprints of the structure of spacetime itself. As black holes spiral toward each other and merge, they generate a distinctive chirp pattern in gravitational waves. The precise shape of this signal depends on how spacetime curves in extreme gravity, potentially revealing quantum effects. Future gravitational wave observatories, both on Earth and in space, will detect these signals with even greater precision. They might reveal deviations from classical predictions, pointing toward quantum gravity effects. The European Space Agency's planned LISA mission, Laser Interferometer Space Antenna, will detect lower-frequency gravitational waves than ground-based observatories, opening new windows on black hole physics. LISA will observe supermassive black hole mergers across cosmic history and track smaller objects orbiting supermassive black holes. These observations will test general relativity in previously inaccessible regimes. Meanwhile, the James Webb Space Telescope is revolutionizing our view of distant galaxies and their central black holes. Its infrared capabilities pierce cosmic dust, revealing black hole activity obscured from other telescopes. Webb is already providing unprecedented views of how supermassive black holes interact with their host galaxies, how they influence star formation, gas dynamics, and galaxy evolution through their enormous energy output. These observations help constrain theories about black hole formation and growth, about how they acquired their current masses and spins, about the mechanisms by which they affect their cosmic surroundings. The upcoming Extremely Large Telescope, ELT, with a primary mirror 39 meters across, will further transform our view of galactic centers. Its enormous light-gathering power will reveal fainter objects closer to black holes than ever before. ELT will track stars orbiting the supermassive black hole at the center of our Milky Way with unprecedented precision. These orbits serve as test particles, revealing the structure of spacetime in the black hole's vicinity. If spacetime near black holes deviates from Einstein's predictions, perhaps due to quantum effects, these deviations might be detectable in the precise motions of orbiting stars. A cosmic test of quantum gravity. Neutrino astronomy offers another window into extreme cosmic environments. These ghostly particles interact so weakly with matter that they escape from regions impenetrable to light, carrying information from deep within. Future neutrino observatories might detect neutrinos produced in the vicinity of black holes. Their energy spectra and arrival patterns could reveal conditions in regions where spacetime curvature approaches quantum scales. X-ray telescopes like NASA's IXPE, Imaging X-ray Polarimetry Explorer, measure the polarization of X-rays emitted near black holes. This reveals the geometry of magnetic fields and the dynamics of accreting matter. These polarization measurements constrain models of how matter behaves in extreme gravitational fields. They provide another test of general relativity and potentially of quantum effects in highly curved spacetime. Together, these observational approaches form a multi-messenger astronomy, using light across the electromagnetic spectrum, gravitational waves, neutrinos, and other signals to build a comprehensive picture of black holes. Each messenger provides different information. Combined, they allow astronomers to triangulate toward deeper understanding, even of regions that cannot be directly observed. This observational revolution has already yielded surprises. The first detected gravitational waves came from black holes more massive than many astronomers expected. Subsequent detections revealed an unexpected population of intermediate mass black holes. The image of the M87 black hole showed an asymmetrical brightness in its ring, evidence of complex magnetic field structures and relativistic beaming effects as matter orbits at nearly light speed. Recent observations of stars orbiting Sagittarius (*), our galaxy's central black hole, have detected gravitational redshift, the stretching of light wavelengths as photons climb out of intense gravitational fields, precisely as Einstein predicted. Yet other observations hint at possible deviations from classical expectations. Some studies of how matter falls into black holes suggest complexities not fully captured by general relativity alone. For instance, the spaghettification of stars being torn apart by black holes, tidal disruption events, sometimes produces more energy and occurs differently than simple models predict. This might indicate additional physics at work. Observations of rapidly spinning black holes suggest they might be surrounded by complex structures of warped spacetime. These ergospheres and frame-dragging effects might enable energy extraction through processes like the Penrose process. Some researchers are searching for evidence of quantum gravity effects in the cosmic microwave background radiation, the afterglow of the Big Bang. These effects might appear as subtle statistical patterns in temperature fluctuations. Others look for quantum gravity signatures in ultra-high energy cosmic rays. Particles accelerated to enormous energies might reveal modifications to standard physics at scales approaching the Planck length, the scale at which quantum gravity should become dominant. Theoretical physicists continue to refine predictions about how different quantum gravity theories might manifest in observable phenomena. This creates an iterative dialogue between theory and observation. As observations improve, theories are refined or discarded. As theories develop, they suggest new observations. This cycle drives science forward, even when the phenomena under study cannot be directly accessed. What's particularly exciting is the possibility of unexpected discoveries. History shows that new observational capabilities often reveal phenomena no one predicted. Black holes themselves were initially considered mathematical curiosities rather than real objects. Who knows what surprises await as we peer ever closer to the boundaries of black holes? What phenomena might emerge from the dialogue between theory and increasingly precise observations? Perhaps evidence for one of the major theoretical frameworks discussed in the previous chapter. Perhaps hints of entirely new physics. Perhaps clues to the nature of dark matter or dark energy, which might interact with black holes in detectable ways. The convergence of multiple observational approaches with theoretical advances creates a unique moment in the history of black hole physics. A moment when answers to some of our deepest questions seem tantalizingly within reach. What these various lines of evidence increasingly suggest is that black holes are not simply regions of extreme gravity. They are windows into the quantum nature of space-time itself, laboratories for quantum gravity. And they're bringing us closer to answering our central question. What happens if you fall into a black hole forever? Whether you encounter a singularity, a quantum structure, a passage to elsewhere, or something entirely different. The answer, when it comes, will not be merely about the fate of a hypothetical traveler. It will reveal fundamental truths about the nature of reality at its most extreme, about the ultimate structure of space, time, and matter. Chapter 10. Forever Falls. We've journeyed from the mathematical predictions of Schwarzschild to the curved spacetime of Einstein, from the theoretical speculations of Hawking to the observational breakthroughs of the Event Horizon Telescope. Now it's time to confront our central question directly. What happens if you fall into a black hole forever? What does current physics tell us about this journey beyond the event horizon? Let's approach this systematically, separating what we know with reasonable certainty from what remains speculative, beginning with the well-established and moving toward the frontiers of understanding. First, from your perspective as the traveler, crossing the event horizon would be physically unremarkable. No local experiment you could perform would reveal that you've passed a special boundary. There is no membrane to detect. The force of gravity would increase as you fell deeper, but not discontinuously at the horizon itself. Only an observer watching from far away would see your image freeze at the boundary. This difference in perspectives isn't a contradiction, but a feature of how space and time behave in strong gravitational fields. Both views are equally valid descriptions of the same physical reality. For a stellar mass black hole, tidal forces would become lethal well before you reach the horizon. Different parts of your body would experience significantly different gravitational pulls, stretching you vertically and compressing you horizontally. But for a supermassive black hole, with its more gradual gravitational gradient, you could cross the event horizon intact. The tidal forces at the horizon of a black hole with millions or billions of solar masses would be surprisingly gentle. Once inside, though, the central singularity becomes unavoidable in classical general relativity. All future light cones, all possible paths through spacetime, point toward the center. The singularity lies in your unavoidable future. This is where your journey would become truly strange. As you approach the center, spacetime curvature would increase without bound. Tidal forces would grow until no physical object could maintain its structure. In this classical picture, your journey would end at the singularity, a boundary of space-time where curvature becomes infinite and physics, as we know, it breaks down completely. But most physicists believe this classical picture is incomplete. Quantum effects, negligible in everyday gravitational fields, should become dominant near the singularity, fundamentally altering its nature. This is where the different theoretical approaches we explored earlier offer competing visions of what might actually happen. Quantum gravity approaches generally suggest that the singularity gets smoothed out at very small scales. The apparently infinite curvature would resolve into a complex quantum structure with large but finite energy densities. In some scenarios, this quantum core might cause space-time to bounce rather than terminate. Your infall would reverse, perhaps ejecting you through a white hole into another region of spacetime. Other approaches suggest the interior might contain a complex tangle of quantum strings or loops, encoding all information about what fell in. Your matter and energy would be absorbed into the structure, transforming rather than being destroyed. Holographic perspectives suggest that falling into a black hole might be physically equivalent to becoming spread across and encoded on the event horizon itself. Interior and boundary would be different descriptions of the same physics. The key insight emerging from all these approaches is that falling forever might not mean what we initially imagine. It might involve a transition from space-time as we know it to something more fundamental. In this sense, asking what happens inside might be posing the question incorrectly. The interior of a black hole might be better understood not as a place but as a process, a transformation of matter, energy, and information. This transformation would unfold not in normal space and time, but in a realm where these familiar categories begin to dissolve, where quantum effects dominate and new organizing principles emerge. If this sounds abstract, that's because it is. We're reaching the limits of what can be clearly expressed in language evolved to describe everyday experience. Mathematical models extend further than words can follow. Yet the mathematics tells a remarkable story. It suggests that rather than being destroyed, information that falls into a black hole might be preserved, though transformed and made inaccessible to outside observers. This preservation might occur through subtle quantum correlations in Hawking radiation, to encoding on or near the event horizon, through transformation into forms we don't yet understand. What does this mean for our original question? If you fell into a black hole, would your journey continue forever? The answer appears to be both yes and no, a quantum superposition of possibilities that reflects the strange nature of reality at its most fundamental. From the perspective of an outside observer, you would appear to slow and freeze at the event horizon. Your image would gradually redshift and fade, but some trace would persist as long as the black hole itself exists. From your own perspective, you would pass the horizon without incident, but encounter increasingly extreme conditions as you approach the center. What happens there depends on which quantum gravity framework proves correct. You might encounter a complex quantum structure rather than a singular point. You might experience a bounce that ejects you elsewhere. Your information might be preserved in transformed form. In a real sense, your journey would not be forever in terms of your own experience time. You would reach something, the quantum core, the bounce, the transformation, within a finite interval by your own clock. Yet in terms of the outside universe's time, aspects of your journey might indeed be eternal. Your information might remain encoded in the black hole structure or its gradually emitted Hawking radiation for the lifetime of the black hole itself. And that lifetime for large black holes approaches the unimaginable timescales of deep cosmic future. A supermassive black hole might exist for 10,100 years or more, far longer than the current age of the universe. Perhaps the most profound answer is that falling forever involves transcending our conventional notions of space and time altogether, entering a domain where these concepts, so fundamental to our experience, reveal themselves as approximations. This mirrors a pattern we've seen repeatedly in the history of physics. Seemingly absolute categories, simultaneity, continuity, determinism, reveal themselves as special cases of more fundamental principles under extreme conditions. Black holes may be showing us that space and time themselves are emergent rather than fundamental, that they arise from deeper quantum processes, much as the smooth flow of water emerges from the collective behavior of countless molecules. If so, then falling into a black hole forever means transitioning from the emergent realm of classical spacetime to the more fundamental quantum realm that underlies it. A journey not through space but beyond space as we know it. This answer may seem philosophically unsatisfying. It replaces a clear narrative, falling toward a central point, with a transformation into something our minds struggle to visualize. Yet it aligns with what our best physical theories and observations tell us about the nature of reality. It reflects the humbling recognition that the universe is under no obligation to conform to human intuition. The question of what happens if you fall into a black hole forever thus leads us to the frontiers of physics, to the places where our most successful theories meet and clash, where new understandings are emerging. And while we may never experience such a journey directly, contemplating it stretches our minds toward greater comprehension of reality, toward appreciation of the profound patterns underlying the cosmos. In this way, the question itself becomes valuable regardless of whether we ever reach a complete answer. It guides us toward deeper understanding of a universe more strange and beautiful than we could have imagined. As we complete our journey to the edge of understanding, we find ourselves not with absolute certainty, but with a deeper appreciation of the mystery. Not with final answers, but with better questions. The story of black holes is still being written in the mathematics of theorists, in the observations of astronomers, in the simulations of computational physicists. Each year brings new insights, new challenges, new possibilities. What remains constant is the sense of wonder these cosmic extremes evoke. The recognition that reality extends far beyond our everyday experience into realms where space and time themselves behave in ways that defy intuition. In contemplating what happens if you fall into a black hole forever, we've touched on the deepest questions physics can ask. Questions about the nature of space, time, information, and existence itself. These questions connect the physics of the very small with the physics of the very large. They link quantum mechanics with general relativity. They point toward whatever more comprehensive framework might eventually unite these perspectives. They remind us that our understanding is always provisional, always evolving. That certainty is rarely the endpoint of scientific inquiry, but rather a momentary resting place on an endless journey of discovery. Perhaps most profoundly, they connect us to the cosmos in a personal way. For we ourselves are collections of matter and energy shaped by the same fundamental forces that form black holes. Participants in the same cosmic story. As you drift towards sleep, carrying these cosmic mysteries with you, remember that your consciousness, your capacity to wonder about black holes and infinity, is itself one of the universe's most remarkable phenomena. Join us again soon for another journey through the stars, as we continue to explore the greatest mysteries of our cosmos. Together, we'll keep looking up and looking inward, finding wonder in the darkness between the stars.